Hello, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Colding, and I'll be your host for today's presentation on Ansys EMC Plus and Charge Plus, What's New in 2025 R1. To submit any questions you have during this webinar, please use the Teams webinar Q&A feature. After the presentation, we will address any submitted questions. Should there be any unanswered questions by the end of the webinar today, we will address them over email. Our speaker today is Kevin Miranda. Kevin Miranda is the lead product manager of EMC Plus and Charge Plus. Kevin is also a principal scientist at EMA with a PhD in atmospheric electricity and computational physics. Kevin's expertise is in atmospheric electricity physics, elementary particle physics, and computational physics. Through webinars or at conferences, Kevin gives regular updates on the development progress of the two software solutions. He's very excited to discuss this update on the latest big development to the EMA physics solvers. Without further delay, I give you Kevin.
Thank you, Matt. Thank you everyone for joining us today. Very excited to show you all the new stuff that we've put in 25 R1. A lot of animations, a lot of new capabilities, but also a lot of new performance improvements that I will be sharing with you. If you have any questions, again, please use the Q&A section in our Teams webinar setup. Also, you can see my email address. If you have any questions, reach out to us through our website or just contact me. A quick introduction to EMA, electromagnetic application. We have a business with 60 plus employees. Our headquarters are in Denver, where Matt and I are located. We also have offices in Pittsfield, Massachusetts, and in Champaign, Illinois. We work on several SBIRs and STTRs with the Navy, Air Force, NASA, and Space Force. We have a lot of expertise in consulting, simulation, measurement services for companies around the world. Our software is not just software, it's software validated against measurements, which is key for being able to use the tools for engineering capabilities. We have expertise in EMI, EMC, in EMP, RF interference, antenna performance, radar signature, spacecraft charging, lightning, HERF, P-static, complex simulation measurement combinations, and then as most recently, multiphysics for plasma modeling, and a lot of plasma physics with our heritage from spacecraft charging. We are also a consulting company. We serve as EMI, EMC expert for many industries: aerospace, military, automotive, rail, energy, consumer electronics, plasma, semiconductor manufacturing. We do a lot of first of a kind scenarios. We engage with customers through the use of the software and through the development of very specific problems and workflows with the EMA softwares. And we also have the ability to do various projects that require clearance. We have a DSA facility clearance, and we have several cleared employees. So if your projects are of that type where you need some cleared people to work on them, to introduce the software to you, we can also do that as well. But we are most, and more than ever, a technology partner with Ansys. We develop EMC Plus and Charge Plus, and we work with Ansys to sell and support the solution worldwide. We've been awarded the Ansys Technology Partner multiple times in 2022 and 2024. Our solutions are Ansys EMC Plus and Ansys Charge Plus. Both have a lot of updates for 2025 R1. And if you haven't been introduced to the tools, here they are. The two tools are in the Ansys Discovery user interface. We have our add-ins that you can see at the top: EMA 3D, M-Harness, and Charge and Power Balance are the tabs that we have to be able to set up the simulation, mesh your model, and visualize the results. EMC Plus is specialized for modeling E3 environments, cables, EMI, EMC, and RF sense. The workflow is optimized to integrate the multi-conductor transmission line theory with a full wave electromagnetic theory that helps us solve electromagnetic effects on very large complex platforms. Ansys Charge Plus is more focused on the multiphysics aspects. We have the ability to model space radiation effects, non-contact ESD, arc and ESDs in various environments and materials, and then semiconductor plasma simulations as well. There's a lot of numerical tools within here. A lot of them have been introduced throughout the series, so I invite you to go back through our webinar series to be able to understand how all those numerical techniques are implemented within the tools. This cycle, 2025 R1, we were very focused on responding to the feedback from application engineers and customers around the world. One of the things that has changed last year was a lot of testing from the application engineering team at Ansys allowed us to make sure that we were able to highlight the key necessary improvements we had to do to the solution. We've improved PCB import speeds and reliability by factor 10, even more. So this is very important for being able to integrate the PCB simulation inside your enclosure, both for EMI EMC concerns, but also for ESD application. We've improved post-processing and 3D visualization. I'll show a little bit more about that. We have faster opening of meshed EMC Plus models. This is a capability that is coupled with our new ability to save the mesh in an external file from the Disco file so that you can ship it out or not with your solution. We have a cohesive materials library across the electromagnetic suite, which means HFSS, which means integration with Granta, things like that. A lot of things that we'll be talking in more details in a little bit. We have more API coverage than ever before, especially for EMC Plus. This is very powerful for dealing with complex models and making more automatic workflows, but also for improving internal testing for integration testing internally to the tool. We've improved the workflow for cable twisting. No more need to split the segment along its length. We automatically solve for this within the solver. We've added some correction schemes for the FDTD staircasing. This is called conformal boundary condition, which I'll show you as well in a little bit. And we've improved the robustness of the ray tracing workflow. Our new ray tracing workflow for calculating ionizing dose has been very popular and has improved more than ever in terms of reliability as well and efficiency. And then one of the most complex parts of the solution suite in Ansys Charge Plus is our advanced plasma simulation using the PIC and fluid solutions with electromagnetics, very complex multiphysics. We have improved simulation speeds. We have introduced new techniques within the solvers to be able to use coarser meshes. I have a lot to show you there that we're also very excited about that speeds up simulation time and convergence of the solutions. Here are some of the headlines, new functions. We're trying to improve a lot on our performance, as you can see. So in terms of new features, it seems like we haven't slowed down in terms of integrating new features across both tools. The ones I will highlight today in EMC Plus are going to be integration with the discovery material rendering capabilities, the subcell multi-thin layer material. So you can now create a thin material stack up in your FDTD simulation. It's going to be a subcell algorithm. Improved user experience for larger models and enhanced 3D visualization performance, as well as meshing visualization. And then the clip plane for voxel mesh inspection. I think we have one of the only tools on the market that allows us to probe the mesh in 3D with such amazing capabilities as a clip plane, as the ability to select meshed bodies and explore specifically a meshed simulation, as you can see on the bottom left here in this enclosure with the PCB, and being able to look in details at how the mesh is connected. A lot of tools are available within the tool to make sure the mesh is as the best as it can be. We've introduced this conformal boundary approximation. This is a beta feature, and I'll talk about this in a little bit more as well, what that means. But this allows us to remove the enhancements of the fields that could be created from the staircasing, this cubic grid With the corners of the Y grid, you may have some field enhancements that you don't want for some application. This allows us to remove that. And then the automatic cable twisting workflow as well. In Ansys Charge Plus, we have performance updates for the radiation ionizing dose ray tracing tool. We have some of these new FDTD mesh visualization capabilities. We've improved our multiphysics boundary conditions. Multiphysics is a complex problem with experts from many different fields coming together to solve a problem. We are coming from the electromagnetic side, and we've taken a lot of inputs from the fluid experts on how to set up fluid boundary conditions. We've applied that nomenclature to both the PIC and the fluid, and both of them are now available in the tool. We've also optimized 3D visualization, introduced 1D sheath models. In the past, for plasma simulation models, we typically used what we called an adaptive mesh layer that would resolve the sheath very finely with some mesh elements. Turns out that some of these problems have such a small sheath that we need to use 1D models to solve them. And that helps us significantly in terms of compute speed, as we don't have to resolve the electron and ion distribution near the electrodes. We've introduced energy conserving semi-implicitization. It's a big word, but it allows us to solve for the plasma with a coarse mesh, even though the Debye length of the plasma may be smaller than the mesh. It's key to be able to get to complex plasma simulations quickly and in a reasonable amount of time. We also introduce a coupling with Maxwell. This is an import of steady state magnetic fields from Maxwell into our tool, especially if you are trying to do magnetron simulations or have magnets in the system that are going to guide an arc in some direction. We can model that in Maxwell and import those fields in our solution. I'm going to dig right away into our Ansys EMC Plus highlight features. The conformal boundary approximation is a surface approximation that we apply to one of our objects in the CAD. It allows us to approximate curved surfaces much better than we would do with the cubic mesh. As you can see, even with a very fine resolution on the sphere on the right, you're going to have a staircasing effect. And this could be enhancing the fields, especially for arcing problems, for example, or air breakdown problems, but also for RF electromagnetic reflections in the system. And so if you want to solve radome problems and kind of effects on that level, it's also critical to be able to handle the staircasing properly. So in case there is some misalignments, as you can see like this, you can actually apply the tool. It's one of our beta features. You select the tool and select the surface on which you want the approximation to happen. And we do that automatically in the solver. So on the right, you see a sphere. On the bottom right, you see two spheres where we're creating a spark between them. You can see that we have some field fluctuation and enhancement between the two spheres due to the staircasing. That can actually change an ESD problems, the breakdown voltage, if that's what you're concerned with. So it is a beta feature. What does that mean? In the EMA tool settings, you can actually select enable beta features. It will show you some of the new buttons that we have in there. Beta features are something to be careful with. They are not fully implemented inside the solver. In this case, this feature would be serial CPU only, but it's there for you to try it and give us feedback if you want to experience it. And then this cycle, we are in 25R2, making it available in parallelization and in GPU as well. So this is a kind of a process that we want to start implementing when we have new capabilities that are critical for a lot of users, that we want to bring them to you guys as soon as possible. But it comes with the caveats that there may be some limitations. But let us know and we'll walk you through them. The cable automatic twisting. You can imagine that the twisting inside a cable will be very important. So how many twists your twisted pairs are going through, twisted triplets are going through along the length of the cable will change any coupling of electromagnetics to the system and change the currents and voltage solutions. Also, if you have various modes that you're exploring in terms of coupling, that twisting is going to be key. The new workflow is now in the solver. The user interface actually doesn't change. It's the same as before. You define the number of twists, and that information is passed automatically to the solver. And what we do is we solve for the capacitance and inductance matrix at each E-grid instead of at the end and at the beginning of the wire. This allows us to solve for the changes in capacitance and inductance along the whole length of the system. This is going to be a stepping stone for a lot of different capabilities in the future, but for now, this was key to be able to implement this in a robust way. We've also introduced a thin layer capability. This was in conjunction with the conformal boundary approximation that we talked about. This is key to be able to solve radome applications and antenna systems with higher capabilities than we've had in the past. So in this case, if you want to model a stack up with very thin layers, where maybe you have some changes in thickness, permittivity, and conductivity that you want to capture on how the fields are being affected, both for reflection but also transmission. This is something that we can do here. And it is a subcell algorithm. It is available here in the materials or the structures definition tab of our tool. And it helps us really get much more accuracy in our field calculations. We've introduced a brand new mesh visualization capability. It's called the clip plane. To be able to do this, we've changed how we render the mesh in the tool. It has a little bit more overhead, but it allows us to do very, very amazing investigation of the mesh within a very complex problem, as you can see here on the right. You can select which coordinate axis you want to look at. In this case, you can slice this car in various different coordinates. You can access this from the EMA 3D ribbon next to the mesh variable grid or next to the mesh button with the purple clip plane tool. And you can click and drag the plane throughout the axis that you've selected. This allows you to really look at what's happening inside your system. Here's an example on our F16 demo. We are looking at the one side that isn't clipped, and then we are now looking at what's happening inside the system. And you can look at the cables where they're being propagated through the system. This allows you to look at the details of any connectivity issues that you may have in your mesh and give you a lot of exploration on how to diagnose any connectivity problems. And you can, as you can see, move and drag the mesh throughout the system to explore various parts. You can look at where your probes are inside the mesh, if they're well connected. You can look at your cable routing, look at the various connectivity between bodies and faces. As you can see here, we can make sure that the approach angle of the cable to the module is working properly and that there is no confliction issues in the system. We've also added the ability to visualize the mesh with and select the mesh elements you want to see based on the structure that you want to highlight at the top or based on the material that you want to see. So on the top here, we selected a subset of the CAD, and we can highlight the geometry based on the CAD that we've selected. So we've removed the whole fuselage of the plane, and we can now see all the different components inside the system. Again, very powerful to be able to visualize and diagnose mesh issues, but also make sure that you have what you expect in the system. One of the key things to be able to solve and create this interface was to make the mesh saved in an external file, as we call it a binary file format. We use the HDF5 protocol, as you can see here. All the mesh is saved in that file, and you can now ship the system, your model, your discovery model, with the mesh or without the mesh, a choice that you can make by sharing this mesh geometry, especially for complex objects. And we're also reading all that information for the rendering from this mesh file, which is much more powerful than it was before, especially when we do these cut planes and these selections per bodies. You have the ability to archive results in the mesh file into a .ema3d object that you can then ship out to your colleagues, or that you can share with us very efficiently if you want to share results. This is one of the archive options that you can find in the settings tab. If you double click on EMA 3D archive file, we will automatically open it with the EMA 3D tools. We have a new material assignment inspection tool, something that was highly requested. You say inspect material. You can use some of the settings if you want to make sure that you display it as you're moving or not. And here, as you can see, we're hovering over various bodies in the simulation. And in the center of the body, we are saying that we have aluminum setup. I can then hide a piece of the geometry, in this case, the enclosure. I can zoom in, and then I can get information about the properties inside the system using the tool as well. Here, we can see that if I hover over the tool, I'm going to get the board and then the PC line in the system, which show us where the four materials are in our tool. In the future, we'll be able to hover to improve this and show you more than just material assignments, maybe also boundary conditions, or even probes and hardness and sources, things like that. But this is already very amazing for our users to make sure that they have the materials they want in the right location. One of the other things that we've improved was the ability, the integration with discovery materials. This is key for many reasons. One of them is Discovery is doing a lot to integrate with other tools across the Ansys suite. So if you're importing geometry with material assigned from other tools, Discovery will keep that material assignment. And this allows us to leverage that capability. The other capability is it allows us to visualize geometry with material assigned much better. As you can see on the top right, it's now the materials are both in your EMA 3D simulation tree, but also in the libraries tree and that if you highlight over, for example, the copper, you will see where in the geometry the assignment is present. It also gives us access to a much more extensive library of materials because all the discovery materials are in Granta. I've integrated with Granta, and then we also have the discovery materials suite. All of them are exposed through our material tool, as you can see on the right here. So if you want to change the type of material, navigate to the definitions section in our EMA 3D simulation tree, and then change the material and access to all the materials that you have in here. We've also added the HFSS material libraries inside our tool. It's very extensive and very powerful for all your simulation problems. The materials in the discovery tree on the left are in the libraries section are the best used for highlighting the location and the geometry. Any changes in the material itself, we recommend using the simulation tree that we've had before. This is also currently only implemented for isotropic and PEC materials. We will, in the future, move all materials from EMC Plus and Charge Plus over to this new rendering capability. We've improved the 3D visualization probe. So in the tool, we have the ability to save 3D field data and air conductivity data in an efficient binary file format. Even though that file format is very efficient to save data, the rendering of the millions of elements from FDTD was difficult. So we've added the ability to downsample spatially the data that you're saving to the 3D field probe. And you can see on the bottom right here the strides that you can take spatially in the grid to save your data and still be able to render render results efficiently in the tool. We've, let's say, applied our windowing capabilities to a lot more results than that we could before. We have two solvers, electromagnetic solvers here that are time domain solvers, the FDTD, finite difference time domain, and the time domain finite element method. These two tools create time series results that if you want to look in the frequency domain, you can use our windowing functions across the tool. If you right-click on your results node, you have now the ability to run those scripts on much more than you could in the past. So this is also very critical to make sure that you get the proper Fourier transforms on your data. There's also another tab in our tool, EMA 3D harness charge and power balance. The power balance capabilities have been updated, where you can choose bodies for cavities now instead of simple geometries. You can also select surfaces for apertures and absorbers. This helps you really take your power balance analysis to the next level. We have new APIs, and we've also improved the software testing at each release. So you can see some updates on the APIs here. The key is that we have most of the UI functions for EMC Plus in our API, covered by APIs. The next step that we're working on that you'll see later in 25R2 is the ability to record those APIs through the discovery script recording. For now, all our capabilities in our API documentation is available in the user manual, and it's very well covered with tutorials and examples. So we're very excited to show you this capability to make your analyses and workflows more automatic. In terms of testing, we have testing of the tool at different levels. This is just to show you that we're working very hard on performance and reliability of the software, in addition to all the new features we're sharing. We have 90% of all the new code covered by unit tests. We have physics solver regression tests that we've been doing for years. And we also now, as of this month, have integration testing of the core UI plus solver that we implemented in 25R2. That's also very powerful for testing the product to levels that that are going to take its reliability to the next level. So we're very excited to provide a much better user experience than we've ever had before. Now I'm going to cover Ansys Charge Plus features. So we're going to go through some of these new fluid boundary conditions, inlets and outlets. This is what I was mentioning by providing fluid CFD experts the ability to leverage the multiphysics the way they would for their physics, the fluid aspects of things. So we've, instead of creating a pick density boundary condition, we now have split the electromagnetic boundary condition, the inlets and the outlets. And you can see the inlets, there's a lot of overlap with how a CFD solution like Fluent would define inlets as mass flow rates, as velocity, density, pressure, or wall boundary conditions. We have no slip, free slip boundary condition. These are all terminologies that are critical to make sure that our engineers can solve the multiphysics problems in Charge Plus. This is an example of how it's done on our Langmuir probe demo. You can see the updates here in the boundaries section where we have electromagnetics inlets and outlets set up. We also have the sheath models. You select the surface, then you go ahead and select the plasma on which you want to apply that in the structure tree, like electrons and argons. And then you can expand the properties section. There's a lot going on because this is applied to both a fluid solver, which typically densities are defined in kilograms per meter cube, but it's also applied to the PIC solver, the particle and cell solver. And so you can change the number density from true or false. This helps you change the units very easily depending on which you want to use for these analyses. When we talk about a PIC particle and cell simulation, we tend to work in number per meter cube versus kilograms per meter cube for the density of the fluid. This all depends on the densities and the type of simulations you're running. In this case, we're able to set a boundary condition at the edge of this simulation space to 1e⁻⁴ for the densities of both the particles. The other ability that we've added to the tool is the ability to select if you want the plasma to contribute to fields in one body or another body. So as you may be familiar with, charged particles are going to create space charge, have space charge, which will create electromagnetic fields in the system with respect to where the ground is present, for example, or with respect to your boundaries in your system. So an electron beam with respect to ground based on its density will have a certain potential that will be generated between the beam and the boundaries. So here you can select in the materials tool which plasma model you want to use, and it will overwrite the ones in your domain settings. So here for this vacuum where we don't want electromagnetics at the top, you can change it and make sure that you don't account for space charge. What does that do? It helps with stability of some of the simulation, but it also will change and be dependent on what your application is. So here we have two simulations on the right based on this geometry you're seeing on the left. The beam is coming from the top, and on the top simulation, you're looking at the space charge contribution in the upper body, while on the bottom, you don't have the space charge contribution. Your beam profile is going to change because those particles are affected by the electric fields. It's a two-way coupling. So being able to model the fields is important, but having the ability to select which bodies is also very critical based on the simulations you're running. Another capability that we've improved on is our meshing. And so here we're looking at leveraging the discovery meshing instead of our legacy meshing. We know that the workflow requires us to, for charge, to create, to tell the mesh engine that we're sharing the topology, because the finite element method requires a conformal mesh at the interface between bodies. So now we can define mesh groups per body, and we can leverage the prepare section of the tab, run the enclosure tool, for example, then the imprint interference model for the CAD, make sure that our geometry is properly ready. And then we use the share topology section to make sure that the mesh engine knows which bodies are touching one another and where we want the mesh to be conformal. And so here, this is one of our tutorials for the Lunar Lander available in the help documentation. You will see that we have a lot less mesh settings with the new mesh engine. All the advanced mesh options are gone. Everything is handled automatically. It's a little constraining in terms of your capabilities of generating a mesh, but it makes it very robust, this workflow, in terms of having quality mesh for your electromagnetic and multiphysics simulations. And so here we're applying body mesh groups, in this case a 5mm mesh on the top features. And then we're applying another mesh groups on the system. Now we can mesh. Our mesh is complete here with about 100,000 volume elements. When you run the discovery mesh engine, the show mesh is going to be on the bottom right compared to the legacy mesh, which had the mesh display in the simulation tree. So don't forget that if you don't see a mesh with this new workflow, it's because you want to look at it on the bottom right and click the mesh visualization tool. And now you can see all the mesh groups that we've applied of 5mm on the top, and a mesh that is ready to go for the simulation of surface charging at the surface of the moon. We've improved the ray tracing capabilities for measuring ionizing dose. The tool has been very popular, and we've gotten a lot of feedback for its capabilities from 24R2, and we've built upon that. One of the things we've done is we've decoupled the solver from the user interface. This allows you to stop a simulation without having to kill discovery, which was a little cumbersome. But this is also allowing us to give you updates of the executable much more quickly if we need to do that. In this case, this is a tool that we're very excited to have, and that helps us solve for the dose, ionizing dose on PCBs and sensitive equipment inside very complex structures like your satellite or your enclosure. You can add very easily additional shielding on the surface of the PCB. And so this is a tool that's been very exciting for us. One of the things we've added is an API to be able to create probes very quickly. A lot of these PCBs have a lot of components, and if you want to solve for the ionizing dose on each component quickly, you can use APIs to create the probes on each of the components. And here you can see that we selected some of the transistors and the IC on the system and assign it specifically to the bodies that were in your CAD. So if you have an imported geometry of your 3D layout with all the components well labeled, you can easily loop through all the components in your set and assign a probe to it. Now onto the plasma simulations. For the PIC and the fluid charge, like RF plasma simulations, we have improved the ability to model the sheath. The plasma sheath is key to solve for the proper electric fields inside your system. If you don't have the ability to model how the plasma is screening the electromagnetic field that you're applying to the system, you're not going to get the right fields, which means you're not going to get the right energy and then not the right ionization densities and etc. for the whole system. But the problem is that when you reach higher densities in plasma simulations, you're going to have a sheath that is much smaller than what is reasonable to mesh. And so in our case here, we've introduced subcell sheath algorithm. They're like 1D algorithms. We have an analytic sheath model that we use all the time for our problems. And then we also have a kinematic sheath, which we call PIC1D 3V, which is a technique that allows us to share macro particles between the PIC, between the sheath and between the bulk plasma, and also between the surface. So we have a lot of tools in-house to be able to tackle these problems, and it really helps us with simulation time. I'm gonna take a 2-second pause here. I need to blow my. Okay. So the other thing that we worked on is a very novel approach to solving for to resolve the issue with plasma simulations when the mesh are too coarse. The problem is called numerical heating, and it's caused when the Debye length is not resolved for the plasma. The Debye length is something that speaks to the interaction of the charged particles with one another. And you can imagine that we're not creating a mesh that allows us to solve for any screening effect between an electron and an ion on a micro scale. So we have to be able to solve that problem on a macro scale. And this is where our EC sim capability is key. This is something that we have a lot of details on, but you can see on the left here, this is a cube with just a plasma that is initialized at in the system. And after a certain amount of time, you can see that we're looking at temperature. The temperature scale is exploding. We are actually diverging, and the plasma is just numerically unstable. But if we add the implicitization capability, as you can see on the right, after the same amount of time, we're actually able to keep the plasma densities and temperatures at the levels that we expect them to be. Being able to solve this with the mesh element that we're using here, we don't have to resolve it with millions and millions of mesh elements, which makes those computations impossible. In this case, we are solving this problem maybe with a mesh size that is 100 times the Debye length, which allows us to get to the results that we need for all these plasma applications. Most applicable here is this example, which is a 2D slice here of the GEC reactor. This is one of our newest tutorials. This is the GEC chamber. In addition to using the techniques I just talked about, we are also have been testing and successfully applied the ability to just create slices, as you can see here, of your 3D model and effectively solve this in 2D with our TET mesh and our existing solver. This speeds up the simulations tremendously and allows us to get to steady state after hundreds of cycles in times that would be very difficult with a 3D simulation that has the mesh resolution needed to solve for all the physics that we're seeing here. In this simulation, we have an electrode at the top and an electrode at the bottom, and we have an RF pulse that is applied to the system. The electrons and ions are responding very quickly at each cycle to the RF applied to the system. And you can see on the right the potentials that are generated by the plasma at the same time as the potentials also applied onto the system. And this gives us a distribution of electrons and ions that we expect with a toroid shape in 3D. In this case, we have an off-center enhancement of the ionization. And this is only doable by leveraging the analytical sheath models that we've applied, by leveraging the 2D mesh capability, and also the EC sim capability. So a lot is going on, and a lot of the workflow has improved for us to get very valuable information out of these simulations. We've done a lot of validation against literature for these argon reactor simulations. We can see the steady state of the ionization rates, but also the off-axis peaks. Our electron energy distribution functions are also the ones we expect, and we're only improving every day the performance of the solver at solving these problems. One of the exciting capabilities as well is the integration with Maxwell. In our domain, in the advanced option, pick options, you can say mapped background B field. There's a little bit of a manual step that you have to do where you export the simulation files, and then you take our nodal information of the mesh that you pass to Maxwell. Maxwell will do an interpolation on that point cloud, and then we can import that file into our tool as a background field for the simulation. It's pretty important because the magnets in, for example, a magnetron sputtering application need to be solved accurately to get the field distribution in the system. And Maxwell has all the tools needed to solve for the ferromagnetics. So here you can see the different poles of the magnets that are present, the different capabilities that we can do in Maxwell. This is part of our tutorial for how to set this up. You have a choice in the magnet types, and then Maxwell will actually go ahead and create the electromagnetic field distribution. And here we can see that when we change the scaling, we're able to see the magnetic fields in the system. And these fields are going to make it through your target. And we can actually import those fields, as you can see on the bottom right, as a background field in our tool so that our electrons and ions will respond to those fields adequately. The other thing that we've really pushed on as well on Charge is the ability to model ESD in the FEM. So we have ESD capabilities in the FDTD, but now we've also validated and elaborated on the ability to model ESD, because in the FEM, we're not limited to the air and humidity that we have in the FDTD. We have the ability to model any gas for which you can source your collision cross-section data. And so in this case, you can get electron collision cross-section data for air, which is what we did, and we're able to model and validate that against actual experiments very well. We are getting breakdowns that are within 2% of the expected results for breakdown voltage, and we're able to see here the 3D simulation of the discharge between a curved electrode and a flat electrode. You don't have the staircasing effects. That's why we're able, for example, here to get to such high accuracy because of the mesh that we're using, which is a unstructured TET mesh. We also have the ability to run this in 2D and 3D, just like we do for the GEC. We have a 7x speed up here in this case between the 3D and the 2D model. Very useful if you want to get to resolutions to simulations quickly, but maybe a little cumbersome if you want to see the effects of magnetic fields and things like that on your sparks. Going 3D is going to be key. Again, I think we expect this to work for many different gap sizes, even very small gap sizes, as we have some physics in the FEM that allows us to solve for thermionic emission of electrons and E-field generated electrons between conductors. And so we're pretty excited to be able to have this. Also, air pressures that are very small. So maybe you're nearing vacuum environments. If you want to look at air discharges in that system, we can do that as well. We've also worked very hard on the solver to be able to model very thin layers along the surface of dielectrics and conductors. This is going to be officially coming in 25R2, but I wanted to show you some of the capabilities real quick to show you that we can do surface flashover simulation for very high voltage electrodes and insulators. And so in this case, we're modeling the fields in the system in the TDFEM, and on the right, we're looking at this variable that we call arc node, which tells us which elements are breaking down. We're even getting breakdown of the dielectric itself, but we're preliminary getting the arcing over the surface and the tangential distribution of the fields along the electrode. And then we get a full arc that you can see also on the left here in the image. Flashover simulations are key for high voltage system, but they're also important for PCBs. This is using an empirical model that we have in our tool that we call the stochastic tree model that we've used for dielectric breakdown, but that we can now use as well for modeling surface flashovers in air. We have a lot of new tutorials in the tool that we've updated, especially for Charge for 25R1, based on all the new capabilities that I just introduced with the inlets and outlets and the new physics capabilities. These tutorials are available in the user manual. We have the tutorial for the 2D slice of the GEC reactor. We have an electron gun tutorial, and then we have an updated electron ESD ESD simulation as well in the FDTD on the sensitive IC that we have as well in the system. I invite you to go through some of these tutorials to learn about the fundamentals of our tools and the complex physics that is present. They're key, and please reach out with any questions that you have on how they work. There's always places where we can take these tools, and they're really meant to set you up on your complex problems that you're working on internally. The other very exciting capability is a development of what we call the VTK plugin, Virtual Visualization Toolkit plugin, which is something that is available in our Pair Review, a third-party tool. Our data is now saved in an HDF5 file that we talked about for more optimized data processing. And this HDF5 file can be parsed directly by third-party tools that leverage VTK. In this case, I am navigating to an HDF5 file, .h5, and I can load different result types that I may have in the tool. I can cache the data into memory if I want to get even quicker in terms of animation and generating animations. And this is bypassing the processing of data into VTK files and VTU files, which was taking a long, long time. This is pretty game changer in terms of data visualization capabilities. And you can select all the data is going to be available within the results file. Here we're looking at a gas propagating through a valve, and we're able to see the thick particles really propagate through the system and even bounce back based on the reflections that are happening at the walls of the system. And this is all happening live in terms of the visualization just by reading the HDF5 file directly that is generated by the solver, which is very powerful. This VTK plugin works for also some EMA for the FDTD, and it's actually a stepping stone for a lot of the animations that we're generating in NVIDIA Omniverse. So here on the left, we have a visualization of an electron gun coming down and creating a air discharge onto the board and attaching to the IC at the same time and generating fields. And you're able to create and really understand how your simulation results look like in real life, which is key to make sure that you get the proper interpretation of these results. I love to show you pretty animations, but I also really like to make sense of my simulation results in a real life scenario. And so these are just a couple examples that our team here at EMA, the EMA Connect team, has been able to put together to be able to visualize how electromagnetic radiation couples to various aspects of, on the left, a board, and on the right, a human body. The last thing I want to talk about for the next 2 minutes is our EMA Expo for 2025 on April 28th and May 2nd at UMass Amherst in Amherst, Massachusetts. We are hosting an EMA Expo for the whole week. Our goal is to bring together industry leaders, innovators, and professionals in electromagnetics and all the multiphysics that I discussed today in related industries. We have key highlights, technical workshops and panel discussions, exhibitor showcases featuring cutting-edge technologies, a lot of networking opportunities with industry experts, special keynote sections, and we're always inviting you to contribute as well to the workshop. It's a great opportunity to present and speak about your expertise with EMA tools. So please reach out and register at the Expo. We are very excited to have you there. On the software side, more specifically, we actually have EMC Plus and Charge Plus expert workshops led by my colleagues and I, where we show you specialized applications of the tool and make ourselves available to give you much more in-depth knowledge of these tutorials that you've seen, but also various workflows that we have in the tool that we haven't even discussed today. This is a workshop that is probably going to be game-changing in terms of taking your knowledge of the tools to the next level. You'll get more understanding of the fundamental concepts, practical applications, advanced techniques, and you'll have hands-on training as we'll be able to walk you through the use of the tool in person. You'll be equipped with all the skills you need to use the tool to make sure that you enhance your product's reliability as well. That's it for me. Thank you so much for your attention, and I hope you we're able to take in all this information. Let me know if you have any questions.
Thank you very much, Kevin. Now that you've completed the presentation, why don't we start reviewing some of the questions that we have received. The first one we have here is, where can I download the 2025 R1 patch?
Yeah, so as you know, the tool is available on your customer portal at Ansys. The patch is going to be available soon on that customer portal, but for now, you can download the patch on the EMA3D website at ema3d.com/quickstart. You'll be able to access 25R1 SP1.
Okay. Next question is, can I run the ray tracing solution on CPU, or is it only compatible with GPU?
The ray tracing solution is only compatible with GPU because we leverage the NVIDIA optics libraries to solve the problem very efficiently and very quickly. So we need an NVIDIA GPU that is recent enough to have access to these optics libraries, and that makes it very powerful of a tool.
Excellent. Next question is, what is a plasma sheath?
That is something that I would invite you to look at some of our tutorials to get a better understanding of. The idea here, and you can see it on the bottom left, this is a Langmuir probe, which means that we have a metal sensor on the inside that is charged to maybe 15 volts. And then we have 0 volts on the outside, which is the reference plasma potential. What happens is when you charge a system, you're going to have particles that are going to agglomerate or accumulate next to that electrode, right? So here the electrons are attracted to that 15 volts that we're setting up in the system. At this density, you can actually see it very well in 3D. This electron density will basically change the field distribution perceived at a certain distance away from the electrode. So that is what a sheath looks like for the electron distribution. If you had ions in here, they would actually be pushed on the outside of the volume. And you are going to have a balance of ions and electrons during that sheath modeling, and it will play a very significant role on what the potential is as a function of, in this case, radial distance from the center.
Excellent. Next question is, the cable automatic twisting slide says the only input required is the twist rate. Does this assume that there is already CAD showing the cable with untwisted wires? Does the solver need to know the routing, gauge, strand count, etc.?
That's a good point. Maybe the slide was a little misleading. Yes, the solver needs to know the gauge. It needs to know the routing that we do through the CAD geometry, but we don't need the CAD of the actual harness itself. You can set that up using our mHarness solution, and that allows us to leverage the transmission line solver that we're using to solve for the cable solution.
Okay. Does the HFSS library have the proper parameters to perform a surface or internal charging analysis?
The answer is that that library has the information necessary to solve for the electromagnetic fields properly, aka the conductivity and dielectric constant. But if you are trying to understand how plasma is interacting with that material, the HFSS library does not have the information necessary, which for internal charging is going to be the density and the Z value for that material, so the atomic number. And for the surface charging is going to be secondary electron yield parameters. A lot of these have to be sourced additionally to the variables that you can get from the HFSS simulation.
Okay. Next question is, for Charge Plus, is there a limit to the particle number densities and particle flows? That is, peak currents, virtual cathode/anode formation, bipolar flows, collective and relativistic effects.
That is something I need to read in the chat.
There's another part to the question, so we can break it up into multiple answers, or we can try to assess it as a whole.
Let me answer the first part. So the way I tend to explain the difference between PIC and fluid numerical solutions, the particle and cell versus CFD, is that you can use particle and cell to solve CFD problems, but at the densities that the CFD is more optimal at, you may have issues to get a computationally feasible solution with PIC, right? The PIC is used for lower densities and the fluid typically for higher densities. So in our case here, we have the ability to run this in hybrid, where we do solve with a CFD solution that is integrated inside the tool. And we also have the PIC solver. I'm not aware of a limit in terms of the densities. Like this example that we're seeing here is about 2 atmosphere for the discharge, and the peak current is also something that is going to be a consequence of your densities that you're solving in the system. And we've actually modeled very dense like metals as well in the particle and cell. So if you want to model copper ions and how they're flowing in a system, you can do that as well. So the density is, I don't think, something that we may have. I don't think we have an issue with that. And then the second part of the question is, are there any examples relevant to the plasma liner B-flux compression, dense plasma focus, or ultrasense plasma charged particle beams? I don't have examples specifically for that. If you have a specific case that you would like us to look at or to work setting up with you, we're definitely available to do that. Definitely, please reach out to Ansys and us. We can help you get set up with some of these models. And then the last one is runtimes for plasma simulations. Again, we're trying to improve that as much as possible. These in the time frame of hours, we can reach steady state simulations for the plasma simulation, which is much more efficient than other tools. So we're very excited to be able to provide that, but it will be obviously application dependent. So we're also looking at acceleration in the future, example of GPU acceleration for PIC, things like that. So there's going to be a lot coming.
Excellent.
And then one more question, I think. We have time. Is it possible to simulate the klystron and traveling wave tube with HF field? So we simulate the electron. We can simulate the bunching of electrons in the klystron, and we can simulate the fields generated by the electron bunches using the space charge capability. And we can also apply electromagnetic fields to the beam to be able to create that bunching properly. The answer is yes, but we don't have a demo for that capability just yet. I think the stepping stone would be to use the electron gun tutorial that we have and then apply electromagnetic solutions, electromagnetic magnets and electrodes along the side of the beam. And then, yes, I think maybe you can take the last 2 questions, Matt.
Certainly, yes. So for those who might be interested in receiving the slides for this presentation, you can certainly do so. Please feel free to reach out to myself or Kevin. We'd be happy to send them to you separately. As far as the access to the recording goes, following today's webinar, all registrants will receive an email from EMA with the link to the recording of this presentation. That link will take you to the EMA webinars archive section of the website, and you'll be able to access not just this presentation, but all of the others that we have in our Solving Electromagnetic Challenges webinar series. Thank you, everybody, for your time. We're now nearing the conclusion of this session. As a reminder, any other additional questions that were not answered today can be addressed via email. If you have any other particular questions about the sections of interest to you in this presentation, please feel free to reach out either through the ema3d.com website or via email. Next up in the EMA Solving Electromagnetic Challenges webinar series is Space Environment and Radiation Effects Lab, Capabilities and Roadmap, which will occur on April 23rd. Thank you all very much for your time and attention. Have a great rest of your day.